These are the frequently asked questions for pre-calculus, and this would be for section 4.5-A2. It says we are going to analyze each function for domain, range, continuity, increasing or decreasing behavior, symmetry, boundedness, extrema, asymptotes, and end behavior. So we're talking about all the characteristics that this graph has, and I went ahead and stole this from the summary in your book so we could take a peek at this as we're going through it. So for number 19, domain. The x values that we can use are everything that are not the asymptotes. So try to figure out an easy way to explain how those asymptotes come to be. So our domain of f, well, let's look. We're at negative pi, at 0, and pi. So pretty obviously, this is going to be in intervals of pi. So we figure out, well, that means our x values are defined as x can't be a multiple of pi. And I'll just go ahead and use n to stand for multiple, where n is from the integers. It's a member of the set of the integers, an element of that set. And that says that we understand that our asymptotes are something we can't use, and that those are numbers that are multiples of pi. Range of the function. Well, we're going down forever, we're going up forever, but we have a gap in the middle, and we've experienced this before with our interval notation. Down forever, negative infinity, negative 1, this time we're including that negative 1, but then it makes a jump, so we need that union notation with 1 to infinity, and that will take care of the range. Now we need to know whether or not it's continuous or not. Well, this is where we say, yes, it is continuous, realizing that, of course, we're going to have to lift the pen, lift the pencil to go to the next parabolic shape that we see. So to explain that, we would say that it is continuous over its domain. And what that says is we understand that we have to make, a jump to a new parabolic shape over those asymptotes. So continuous over its domain. Increasing versus decreasing, not so easy, because as we do that, we realize, all right, we're increasing here, we're increasing here, we are increasing here, and we are increasing here. So how do we tell somebody that that's what's going on? Well, we have to break this up, because if you look at just the top portion of this graph, everything that's above the x-axis, we'd see that it's the same group that is always repeating as we go through. And it's the same thing with the denominator. It's always going to be this piece right here where we see that increasing behavior. And this one, it gets a little bit for you to see what's going on. But notice this is negative 3 pi over 2. This is pi over 2. And hopefully you start to see that we have odd numbers of pi over 2 for all of these. So for the ones on the top, we would say on each interval, centered at x equals pi over 2 plus 2n pi. So when that interval is centered at pi over 2 plus 2n pi, where n is the set of all integers, well, then we have to take a look and say that is what we have above the x-axis. And so we're going to have to say that the left-hand side of it is decreasing, and the right-hand side is increasing. And that's exactly what we're going to say. So it is decreasing on the left half and increasing on the right. And then we need to figure out a way that we can explain what's going on with the bottom half of this graph, everything below the x-axis. So again, you go back and you say to yourself, okay, where is this, the bottom portion of this graph, centered at? And we have a negative pi over 2 and a 3 pi over 2. And again, we're seeing those odd multiples of the integers up on the top. And so for these, we would say on each interval, centered at, and we want to see that 3 pi over 2 show up, so we would say x equals 3 pi over 2 plus multiples 2n pi, where n is the set of all integers. And if we just keep putting different integers in for n, we will see that that's exactly what we need to make that work. But now this is going to be backwards from the top portion, so we're going to have to say it's going to be increasing on the left half, and decreasing on the right half. All right, that's increasing versus decreasing. That was probably the longest one out of all of this. So next thing to do is remember that cosecant is what we get when we flip sine. Now why that's important is because of symmetry. It's going to have the same symmetry as the sine graph, so that is odd symmetry. So the cosecant of negative x will equal negative cosecant of x. Then they wanted to know about boundedness, and we can see from our arrows that we are going to be going up and down forever. So this one does not have, it's not bounded above, it's not bounded below. So we can just put no, there's no boundedness there. Extrema, yep. On the top half of this graph, we have a lowest point, and that lowest point is 1. So it's a minimum of y equals 1 at. Well, then we need to figure out how are we going to explain where that is. And we actually did that earlier when we were figuring out what we should use for the increasing and decreasing behavior. Because if we go back to the graph, we see the negative 3 pi over 2 and the pi over 2 as being the center, and that's where that 1 is going to be, centered between those asymptotes. So extrema, where the minimum is y equals 1 at, x equals pi over 2 plus 2n pi, where n is the set of all integers. Then the max is going to be negative 1. And again, we just go back and say, okay, well, when is that happening? Well, that's actually a negative pi over 2 plus 2n pi, where n is the set of all integers. And then we have asymptotes, which we have to describe, which we basically already described with the domain, except what we said was those vertical asymptotes were what we could not include for the x's. So it's the same as the sine of x equaling 0. That's exactly where we get those asymptotes from. So that's going to be x such that x equals n times pi, where n is an element of the set of integers. All right. Oh, there are no horizontal asymptotes. That's what we see with all of our secondary trig functions, our cosecant, secant, and cotangent. And then the end behavior does not exist. End behavior does not exist. We know that you could stop at one particular place and talk about where the graph is stopping, but we're saying if this continues on in both directions forever, we have multiple places that it could end up. So our end behavior, we just have to say it does not exist.